Okay, so before I get started, I think I'd like to talk about some motivation. And this is what motivated my research. I think many of you who like theory don't need to be convinced that it's useful, but sometimes it happens that you get excited about some theory and you tell somebody, hey, I got this great new, understanding of deep learning. And they say, well, is it going to help me get an extra benchmark? Am I going to beat the benchmark? Am I going to go faster? And sadly, there's no guarantees that it will. There's so much going on with incremental progress. It could help you. It could be an insight that helps you, but you could just as easily get an insight from other things that inspire you to improve your work. So then if it doesn't help you, get a paper published tomorrow, what is the good of theory? And again, I think if you already like theory, I don't need to persuade you, but your friends might be saying, what's the point? So for me, it's to a deep theoretical insight, not that I have one, but the goal for what we're doing here is that it'll allow us to make progress in areas that we really can't make progress yet. So for me, if I can prove something about deep learning, it's not the details of the proof that matter, but rather that it gives a possible mechanism to explain why an algorithm works, and that if we understand the mechanism, maybe that'll allow us to make it work in other settings. So the story here is about semi-supervised learning giving a mechanism that we didn't have before with supervised learning. Okay, so if you think of a motivating problem for semi-supervised learning, there's people here working in brain imaging and pathology where the data sets are not ImageNet and where the problems don't work yet. So if we can understand what makes semi-supervised learning, what do we need to make it work? Maybe that'll help us with that problem in particular as an example. Okay, but for me, when I started, reading about machine learning, I was actually pretty confused a lot of the time because there's a lot of words you hear about that you don't know what it means in deep learning, and then you go look it up in a book and it means something in, traditional machine learning, and it doesn't always match. So we have this picture of underfitting, fitting, and overfitting. And there are proofs. We can prove things about when will a model that we train fit the data, when will it overfit, or does it overfit, or can we prove it won't overfit? That's what in-distribution generalization is about. Now, for shallow models, the textbook models, we can prove that they don't overfit, which means they will generalize. The accuracy on the test set, on the training set, is a good proxy for the test accuracy. But for deep models, it was actually a debate. When I got into this field, it was a big debate. So let me talk about a little bit about the theory. I'm not going to talk about this, but just because, actually, I have a question for the audience. Does anyone teach generalization theory in Montreal? Are there courses at other places? You teach it in your
I do, but not this year.
Okay.
I have a crash course of 6 lectures.
I see.
Yeah.
Okay. So for people who've seen a little bit, the more common textbook stuff is VC dimension. A lot of people have heard of that, but it's possible to use VC dimension, but it's more geared towards discrete models. The definition is very discrete. The appropriate definition that's less well known for, let's say, differential or vector models is Rademacher complexity, which I'll get to. But, less than 10 years ago, there were people in 2017 trying to prove, yes, deep learning models generalize because their complexity is not too bad. Okay? And people thought that would explain why they work. But then at the same time, a really interesting paper came out that said, no, you're wrong about that. Deep learning models can overfit in a very intuitive way. So they said, now it's not to say they will, it's just that they're capable of doing it. So they're capable of fitting, your data set, but also you can randomize the labels and still fit the data. Okay, and that's what this paper was about. And the quote from the paper is, many neural networks can fit the training set with random labels perfectly. This is a trivial upper bound on the Rademacher complexity that does not lead to useful generalization bounds in realistic settings. A similar reasoning applies to VC dimension, etc. So what's up with fitting random labels? Why does that matter for generalization? Well, you could imagine this thought experiment that you take a bunch of data points, split them into two halves. In one half, use the true labels. In the other half, make all the labels wrong. Fit that full data set. Okay, now you've got a neural network. Now you don't train that neural network at all. You just evaluate it on the good half. So you have perfect fit. But now you call the other bad half your test set. So it could be, it's theoretically possible that this model perfectly fits your training set and perfectly misfits your test set. Okay. So again, it's not to say that they do or don't overfit. It's just to say that this mechanism of hypothesis space complexity won't work to prove generalization. Okay, so the actual test that they do is very close to the definition of radiometric complexity that we may get to later. And then in that paper and a follow-up 4 years later, it's not very often that people have a follow-up paper to their own paper, and they just added the title, "It's still." They say it's still important, what we were talking about 4 years ago. Data augmentation is significantly more powerful than than other types of regularization. Okay, and so this really excited me at the time because I just thought, wow, wouldn't it be great to try and prove something about neural networks in this way? Maybe data augmentation. But the problem is, it doesn't fit with all the textbook stuff. So, some people say, well, what's data augmentation? It's taking a data point and giving you another one. But that's not IID anymore. It could be very closely related. So I didn't see how to squeeze data augmentation into supervised learning theory. And then I dug around in semi-supervised learning theory, and there really wasn't much. Maybe something on SVMs, getting a better guess to the margin, but really wasn't too good. However, people have come along and had a lot of good ideas. That's what I want to try and talk about today. And so here's the intuition for what we'll go into in more detail. The intuition is, rather than say data augmentation is like new data points, think of it as a form of regularization. So you give me my labels and you try to fit them, but in addition, you have this term here, which is saying if Z is an augmented version of the image X, I want H of X and H of Z to be as close as possible. Okay, so that seems to make sense. I want it to agree on similar images. And we'll see that, we'll basically see that this works for proving what we want to prove. Okay, so the approach we'll take is towards semi-supervised learning and algorithmic stability. So I want to get into that, which I think will appeal a lot to this audience. It appeals to me. But first, this motivation is not the definition I'm going to use. It's just to warm us up. Okay, so let me give you an example of a linearly stable algorithm, okay? So it's just minimizing mx or mw minus b squared plus a regularization term lambda times w squared. But the inputs, m is fixed. We're just inputting in b. Okay, so you solve this, you define the algorithm to argmin, and you get a formula, W, which is complicated, but it's a matrix times B. And using that formula, you can estimate the norm, A of B minus A of B prime, in terms of B minus B prime and some matrix norm of the operator. Okay, so that's linear stability. Make sense? I'm estimating, yes?
What's B prime?
B prime is another different B.
How is it different?
It's just any vector B.
Okay.
So in this case, it's just any vector B. I can tell you how different W is based on how far apart B is in the 2 norm. Okay? So that's linear stability, which is, that's its own thing. But what we need for learning algorithms is nonlinear stability. And the next example will show why. And later we'll see why exactly this is the right kind of stability. So now, okay, so now we're given a data set S, which is pairs of data points X and labels Y. Okay, and there's M of them. And we're going to consider a very similar loss, but now it's a function of X and Y. So argmin of the loss, okay, we're trying to find the W that best fits the data. But when you minimize this, it's the same formula, but what's different is that M wasn't changing before. But X is the data matrix. You change one data point, it changes X just a little bit. Okay, so both the inputs, Y, and the operator changed, but only a little bit. Now, maybe there's a way to do linear stability on this, but you don't have to. Oh, okay. So we're not going to get to it yet, but you can still show stability, and it's using really beautiful convex analysis, which is probably of all the proofs I'd like to do today, my favorite to do. Yes?
Interrupt you, but
Yeah.
this,
I just wanted to, why do you call it linear stability, especially if you go back to the previous version where you just look at the fact that the operator was Lipschitz continuous, right? So here, this is what you
Because
call
the solution
stability.
operator is linear.
Yeah, but the fact that it's Lipschitz, this doesn't have to do, it doesn't,
Oh.
this is just stability. Why you call this linear stability?
Oh, that's just a phrase. It's not
Okay,
important.
yeah, okay,
Yeah.
fine, right. And
But-
you would want the same property now for the next one.
The stability we
might
want
not be.
now is a different, it's not the 2 norm for B. Now it's the replace one, it'll be replace one stability where I change one data point. And what I say at the top that I'll get to later is we're going to actually prove that we can control how much W changes compared to one data point. But the thing we ultimately care about for generalization is how much the loss of the model changes. But that'll follow. So it's a little subtle, but yeah. But this is a major tool in this paper by Bousquet and Eliasif. I don't know if I'm saying the names right. Yes. Okay, so this is just a preview of stability. But I see people seem a bit confused. Is everything okay? Yeah, okay. Yeah,
we have also a question online.
So there is a question on Anne asking, is based on that equation saying the system is linear stable is being C Lipschitz?
yes, yeah, that's right.
Thank you.
Again, that was just a motivated example to show that sometimes we could just write down the equation, but it's going to be a little trickier for a general loss. Now, there's another thing going on here. So other people talking about semi-supervised learning bring up a condition. So this is the idea of label propagation. I see my graph. I have labels, one blue and one red label, but a bunch of nodes connecting them. And the idea of label propagation is that if similar points have edges connecting them, I'm going to propagate the labels and use some kind of a loss to deal with a tie break or when the labels dis. And there's 2 themes that are going to come up. One is a kind of covariance coming up, like a PCA type loss, and the other is graph Laplacians. Okay, so we'll get to that. That's just the preview. I'm going to skip it ahead of this. Now I got to see if I'm able to switch. Okay, so what's the principles behind semi-supervised learning? Semantically similar images should map to geometrically similar vectors. Okay, so we have vector features. They map data to a vector. And let me start by contrasting what's happening in supervised learning. So in supervised classification, let's say we just have K classes. K could be big or small. Then the label's represented by a one-hot vector or an index, right? And what you're trying to do is just minimize a loss like this and potentially learn one weight for each label function, one W, Wj, for each of the possible Ys. That's just the normal setup. It's just giving you some notation. But if we're doing unsupervised learning, let me give some examples where there are possibly an infinite number of labels, right? So if it's face verification, I might train on 10,000 faces or more, but I want to, zero shot, I don't know if that's the right phrase, I want to be able to match a new face and determine if a new image of a face is the same person or not. So that's another label function I've never seen. And similarly, in an algorithm like SimClear, I want the label I'm trying to learn, the function I'm trying to learn is, if you give me two images, are they two different views of the same image? Are they two different data augmented views of the same image? Now, I want to be able to do that on an image I've never seen. So there's millions and millions of images. How do I do that? And the way is, instead of learning a label function for each image, which is impossible, a new weight vector, you use something like cosine similarity or just the dot product. Cosine similarity is often used. So I'm asking the dot product of the features, the two images, to be close to 1 when their labels are the same. Now, it's possible that the y's, there could be, two different images giving the same data augmentation. So there might be, again, some disagreement, and we have to have a loss that breaks ties. Okay, so it could be like perfect clustering, where the y's never overlap, or once in a while, I crop two images of different cats and I get the same. Okay, so this is kind of the heuristic for the features we want. Okay, any questions about that so far as a setup? No, okay. So now here's a picture of this idea. And there's, now forgetting about the losses I'm talking about, people have observed there's a bunch of different ways of getting these semi-supervised learning features. And there's two principles that come up, and I'm using this idea of alignment is one, and the idea of not collapsing is another. If I have a loss that makes constants, like that regularizer I showed, unfortunately, is 0 if everything's a constant. So I need to prevent collapse and find different features. One way to do it is to ask for the vectors to be orthogonal. Okay, and there's a beautiful figure that Arna made from our paper, which I'll get to our paper later. But so now in this 2021 paper by Hao Chen, we have this idea, this formal notion of the data augmentation graph. So I'm going to go into this a little bit now. Wow, it's a lot of text. Too much, sorry. Let me just say it in words that what this is trying to capture is that you take two different images, X and Z, you do all possible data augmentations of them, and then you see how much those overlap, and that defines the kernel. Or you go backwards and say, give me two images and go back, and how many times are they data augmentations coming from the same image? And that also gives you a kernel, and they're related but different. Okay? And the other thing you want to do, or you may want to do, which you can do with every kernel, is just normalize it, because these numbers might get really small because there's not much chance of any overlap. So you just divide by its own norm squared so that k of xx is always 1. That's something that you can always do. So that's what I'm trying to say here. And so the loss that they came up with is something like this. So imagine you do this laborious process. Every time you have two images, you do 1 million data augmentations and you search through and see how similar they are. That's the kernel. And then I say to myself, do this on all million images, all million by million pairs, save that giant matrix, and now find a feature vector whose dot product matches. Okay, that's not a practical algorithm, but you could at least do it in small cases, or at least say this is the loss we want. And so it's argued that that is the loss that we're trying to do, theoretically anyways. But it's not obviously how you train. Yeah?
I have a question. Can we just hear your line?
Thanks. I have a quick question. Can we, for like the next version of this proposed algorithm or something similar, just replace the kernel itself or kernel metrics by learnable free kernel can be just represented by an embedding in different space with dot product on this.
Yeah,
approach.
so I think you're going in a direction that I was hoping some people might go in. So I presented this as, you know, an ideal, but now let's dig into what would be more effective ways to capture the same features, right? And you could think of a lot of things like bootstrapping off of old ones too, which I also thought would be an exciting thing to do. I'm going to provide just a shorter version of one thing that you can do.
Okay, cool.
Yeah. So PCA type losses. So actually, so to understand what's going on with this, which is kind of fancy, I want to just take a step back and go back to PCA. Okay. So for PCA, just regular vector PCA, we have a data set of M vectors in Rn. And I'll confess, even when I teach this, I find it kind of frustrating. I never know which is X, XT, you know. It can mess you up, so I'm always a little bit careful. Now, the covariance matrix is this matrix of XX transpose, so that's the outer product. Now that is an n by n matrix. N is like smaller than n usually. And now we're going to define the loss. So this is kind of an abstract loss of choosing a subspace A and projecting onto that subspace. So I choose some subspace, I might need a basis to do this, and then I project each vector onto it. And now there's a nice proof that there's equivalent PCA losses. So I have a reference to a book there. And basically, you say that if you take an orthonormal basis for that subspace, then you can write that loss up there as follows. It's just the trace of C minus VTCV. So the projection of those vectors onto the covariance matrix, which means that minimizing the reconstruction loss is the same as maximizing the directions of these orthogonal vectors projected onto the covariance matrix. And that latter thing is almost the definition of the top k eigenvectors of the matrix. Okay, so it just pops out from a reconstruction loss to something like minimizing reconstruction or maximizing this covariance projection. Yeah.
Essentially maximizes explained variance, right?
Yeah, exactly. And it's a nice clean proof, and I've looked at many different versions of it trying to pick away at what's going on. And the main thing is when you expand that term up there, you get some cross terms that are not immediately obvious to be zero, but they work out to be zero because of projections and orthogonality. Okay, and to me, this kind of inspires me to think about, well, reconstructions, encoders, decoders. Is there a nonlinear version of this? Okay, so the other result is, and this seems relevant to the type of algorithms we're thinking about, it's not easy to make a bunch of things orthogonal in high dimensions all the time, exactly. So what's a way of dealing with this loss if they're not quite orthogonal? Anyways, this result is not exactly that, but says you could have an encoder matrix and a decoder matrix and minimize this loss instead. And if you do minimize it, what you get is the original projection back. So the minimizer is by taking V, U and V, transpose of the, well, maybe just what it says there. V is the matrix of the top P eigenvectors of the covariance matrix. And you take W equals V and U equals V transpose. So then you get the projection back. Okay, so that's nice. How does it relate to what we're talking about now? Oh, before I get to that, so I'm kind of imagining we're going to do a more general version of PCA to get understand these losses. Okay, but first, what could you prove just from PCA? PCA is basically the nicest algorithm you could ask for. Okay, it's very stable, so it'll turn out that it's stable in the sense we'll define later for generalization. It generalizes in the sense that if you're talking about a sample matrix and the true population matrix, you get the same operator in the limit of taking more samples. That's what it means for the PCA matrix to generalize. And what I think is cool too is that it tells you now, if I give you a vector, I can break that vector into signal and noise. Right? The stuff that I keep when I project onto the top eigenvectors is the signal, and everything that's left over is noise. And if you think about that for a second, it'll even suggest which vectors you could learn with your PCA features, right? The ones that are not noise. And that's kind of a preview of what we're going to see later in a more general setting. Okay, another thing I have to mention, this is related to this K that I wrote before, is that you can build the gram matrix, which is xi.xj, which is a huge m by m matrix, or you can build the covariance matrix. They're transposes of each other. So they have the same information inside, but one is very, very big. Not as good for our algorithms. And so maybe what we want to do for these features is work with the smaller one.
Which one is
Which one is, well, I have
T low n? What's the
my M, many, many samples, so millions of samples in dimension is 1,000, say.
No.
So the feature dimension is smaller than the number. Yeah. And we can make the feature dimension even smaller because of the optimality of the top K. Yes?
Yeah, I'm just wondering in the context of SSL,
Yeah.
it would be great if we, but fairly non-trivial, if we could just divide our space that we are operating into two subspaces, like one regarding the semantical features of the image, like labels and stuff like this, and the other one regarding just some augmentations, Gaussian blur, like the space, subspace and co-subspace to end up with this. Do you think about that, or how to this case?
Can you repeat the question for the?
Okay. Yeah, so the question was, wouldn't it be great if we could, I think you mean like decompose orthogonally the space, our data into purely one and purely the other, like invariant to all augmentations and vice versa. I do think about that. Yeah, that would be great. But I don't have a lot to say about that just yet. Okay, so so now what's going to happen is I'm going to try and take what we did for vectors and replace vectors with functions. So the top K functions. The functions are, some of the time we're going to think of the functions as vectors in a Hilbert space, so treat them that way. But some of the time we're going to think of them as functions actually, which map data to a number. Okay, so let's go back to this loss that we saw from this Hao Chen paper. Oops. So there it is. Why is that a PCA type loss? Well, so the K is already a covariance type thing, right? That's a kernel. And this is f of x is like f transpose, f transpose, essentially. So you plug in two x's and you get a similarity. Now there's another thing we can do. Instead of plugging in two x's, and then we have many, many pairs to deal with, we could plug in two functions. Plug in two functions and see how similar they are. So we could dot product the functions and sum it over all the data. That's the inner product in L2 of rho. But we could also do something to those functions first. And that's what we're talking about. So this T sub m is what happens. This is what we do actually when you pass pass an image through a bunch of data augmentations. And now I've got 20 data augmentations. And then I pass it through my features. And then I average. So that gives me that function gives me the features averaged over the data augmentations. And what it turns out is there's another one, which is the K operator, which is convolution with the kernel, which is not tractable, but it's still well defined. And what we show, which I'm not going to show here, but it's not a super hard thing to show. What we show is that this data augmentation averaging operator, when you take it and its transpose, you get the two different kernels of interest. Okay, so we've factored the kernel. It's already there. It was already there the way it was defined as do a bunch of data. So it's what happens. You take two images, you do a bunch of data augmentations, you get this cloud, and then you average them. We're just doing our averages in different orders.
What's TK that? TK that?
It's just whether the two different kernels are whether you're doing your data, you're starting with two original images and augmenting them to be augmented images and then comparing the cloud there. Or if you're doing reversing the direction of the operators and saying where they came from. So SimClear was the latter one, the way it worked. But some of these other algorithms are using the forward kernel. Just depending on how you set stuff up.
Adam, maybe
Yes.
can you give a bit more intuition for the TM operator that you defining?
Yes, absolutely. So you give me a single a function, like a scalar valued function, and you give me one image. And so f of x is just the value of the function of the image. Now what I'm going to do instead is, the way it's written is, the way I do data augmentation is I randomly choose a number of data augmentations, and I get a bunch of images, which are called x0. X is the base image. Now I get x0. Now I evaluate the functions on x0, and I would just average them in this case. But in the limit, it'd be weighted by the probability. And so that's what we do in our algorithm. Instead of the loss we saw before, and instead of the loss you saw before that has a kernel, what we're going to do instead is take a feature, smooth it by data augmentation, and measure how much that function is close to that, to just f of x. Okay? And now if you put, if you go tm adjoint tm, you get the kernel out. So that's a good thing. But written this way, it's an operation that's very natural to do. There's no comparison of pairs happening. The problem, though, the bad part of it, let me just finish, is that constants. You get constants all the time. So just like with many of these losses, you need to do something so that you don't get all constants. And when I thought about that problem, I thought about the same issue in PCA. Right? The same issue in just finding eigenvectors of a matrix. Okay, so the sort of algebraically, it's easy just to impose orthogonality, but that's not a constraint that's very compatible with SGD. So as a theorem, this works great. In practice, you still need to deal with the collapse, and there's different ways of doing it. Those are, I would say, more algorithmic issues. But I've thought about it a certain amount, and I realized maybe the important thing, kind of like we saw in the PCA thing, is abstractly, you don't care. You care about projecting onto the span of the vectors in PCA. It was the A that really mattered for the loss, not the way that you represented it with basis vectors. And in the same way, as long as you're doing enough work to get good features that span a good space, that span the top k eigen functions, say, it doesn't matter if they're genuinely orthogonal. So that's good. That's good.
So Adam,
Yes.
just I'm getting a bit confused with the notation. If you go up a bit,
Okay.
just to be clear, when you define TM,
First off, it's impressive that you're following the notation.
so so here it's expectation respect to x0 sample from p of x0 given x of f, right? There's no, you don't multiply f by the probability, because then you have probability appearing
Oh, I
twice in
see. Yeah, that's
expectation, right?
bad notation. You're right.
Okay, all right.
It should have said, yeah, so it's just to say what, yeah, it should be a sum p of x. Yeah. So what it's supposed to be in practice, the way you evaluate it is just average over the images, the function values.
I have so my question was about the final objective you ended up with.
Okay.
And so basically, if I understand correctly, you're trying to minimize
So let's call that an invariance to data augmentations.
Yeah. So you're trying to say that under this metric, augmentation just minimally changes my data points?
Yeah.
In some
My
sense?
my features. My features. The features of the
Right.
original image
Right.
are close to the average of the features over augmented images.
Okay.
Yeah.
Okay. Thank you.
Okay, and so in the paper, we got some nice results, but maybe in the interest of time, I'm gonna, I should give some time to the results. So it's partially true that the theory suggested the algorithm, but to be honest, Arne already had some good ideas, and the theory, went back and forth to back it up. But there were two main concerns with the existing algorithms. One was how many data augmentations people were actually doing. They were just doing one, which doesn't seem like enough when you look at the definition of the operator. One is a lot different from all. So we said, what would happen if you did 2 or 4? You need to do more data augmentations. How does it help you? And what we found is that with more data augmentations, you could actually use less data, so less unlabeled data, which is cool. And it worked pretty well. The other issue that people were fighting about, and which seemed to be, if I got this correctly, really slowing down training times, was that when they changed from one loss to another, the original paper used a really huge projector dimension. And Arne's intuition was that this was perhaps because the functions, the span of the function space wasn't great. So you needed a higher projector dimensionality to pick up on the good stuff. And that suggested that maybe better orthogonality would help us get away with lower projector dimensionality. And that also worked really well. And then these results scale to larger data sets as well, but haven't plotted that. Okay, how much time do I have? Is it a hard cutoff at 2:30? I'll aim.
20 minutes, but you
Okay.
over time 5 minutes.
Okay, sure. Let me get to. Okay, so now let me show you one formula. Yes.
So I'm assuming this is a framework for segmentation. What if we're doing some segmentation so that in that case, want to have all the augmented features to be the same because then something rotated to that feature.
Okay, yeah, so that's a point that we were discussing. There were a few of us. So a few of us were discussing data augmentations. So this assumes, implicitly assumes that data augmentations preserve label invariance, right? But you may care about more than one type of data augmentation. You may want to make distinctions using data augmentations and build that into your features. So I think that's an important thing that needs to be done. But it's not, I haven't seen a loss that does that yet. It's good to think about. Absolutely. And people don't even name it, right? They don't even say. So I wrote down that the labels are invariant, but it needs to be explained, right? And there's other questions related to that too that are super interesting, like how do you find the right data augmentations? Okay. So at the same time, it hasn't been that long that these algorithms have been around, and understanding even the basic algorithm, I guess that's more what I'm trying to do from a theory point of view. So I spent a lot of time. So here's a personal story, just in case people are falling asleep with all the math. So our paper got scooped by this guy. I'm sure it's never happened to you guys, but off the record, I guess it's being recorded, so I can't say off the record. But basically, his paper was really good. It had better results than ours, and it came out at the same time. And some of us believe that he was also the referee for our paper. And so it didn't go that well. But you have to get over these things, especially when you have a job. You can't complain that much. So I thought, let me read this paper. And in January, I started reading it. And this is equation 1 of his paper. And it seemed like the key part of the whole thing, because when you look at the rest of the paper, it's a lot of boilerplate generalization theory. I'm not an expert on that, but I can get the gist of it. What is this formula? And all he says in it is this one sentence. And I didn't see this thing, and also this paper, it doesn't look like, math to me. So I'm old, so when I try to read these deep learning papers, I try not to read it too much and just get the gist of it and then think about it. I didn't read Hao Chen too carefully. I didn't understand this formula, and then it took me a long time and I figured it out, so I want to share that with you. And I think it's going to be useful too. It wasn't a waste of time. So this is the condition that the target functions need to satisfy in order for them to prove generalization results for the features that come from the loss, really any SSL loss. I thought, well, that's great, because that sounds like deep learning that generalizes. Okay, but the condition is confusing. So there's the hint. There's this picture we talked about, again, the intuition. I won't repeat it. It's just there to see again. So I used to love graph Laplacians, but I didn't remember them. But I found this book and I started reading about it, and this is what I saw. So you have a graph with vertices and edges, and the edges have weights W. Okay, that's the setup we're in with semi-supervised learning. Now, we can define, for a function on the edges, we're going to define its weighted L2 norm, right? That's a pretty normal thing. It's just h of e squared times the weight. That's pretty natural on edges. You can also rescale things, divide by the square root of W to make things unit vectors. That's important because there's more than one way of doing this, but it doesn't matter too much for our discussion here. Now let's define an operator that takes functions on the vertices to functions on the edges. Okay, so you could have 10 vertices with 30 edges, and what you get is the gradient operator takes f, you give me an edge, and I give you a number. And what's the number? It's f of the plus edge minus f of the minus edge. That's the gradient operator. And now I'm going to define, I can scale it if I want. I'm not going to focus on that too much. And now I can define for a function on V a semi-norm. It's almost a norm, which is just this. You take the gradient of G, so now it's a function on edges, and then it's L2 norm. Okay, and that's the formula. And that's the formula from, which maybe I should have seen it right away. That's equivalent to the formula 1 in the paper that was confusing me. Actually, a little bit more. You do the Rayleigh quotient, which is then you divide by its norm on V. Just normalize it. And that's this formula when you interpret the edges to be probabilities of a data augmentation. Okay, I don't know if it's plausible. I've tried to use notation that makes it seem plausible. So what? Let me go back up to our motivation. So in our motivation, what's happening is if I color this badly, and there's a bunch of red and a bunch of blue connected by edges, then when, let's say red is +1 and blue is -1, when I do the gradient, I get a big 2 across a lot of edges. I square it, I add it up according to the weights, which are all equal here. I get a big number. So that means this operator hates functions that disagree when there's an edge attached. Okay. It's also quadratic, and it also is almost invertible if you, as an operator, the thing transpose itself. The only problem is constants vanish. So if we could just take away the constants, it'd be invertible. And that's what we're going to do. What are we going to do with this thing? So I'd like to say that by using this term, this Laplacian, well, first off, Runtage already proved generalization, but the way he did it was using technical stuff from Wainwright about non-parametric function classes and complexity of them. I'm going to argue for you that you can do the same thing with stability theory, and I prefer that technique. And the stability, the operator that's going to make things stable is this n of h. It's just the gradient of h norm squared. That's what, if I had time or another lecture, I would try to fully convince you of. Instead, I'm going to just sketch it. So there we go. Oops. Okay, so so I'm not going to be. So what I want to do is just outline in the time we have some of. Now this is grad course material that you may have seen in Yannis's class or heard about, but which will get you most of the way to the theorem you'd like to prove. So it's textbook stuff now that will prove this result. The first thing, so I'm going to maybe go a little medium fast, but just to get to hit some of the main points. So the first thing is just to talk about random variables and concentration of measure. So first, convergence of random variables. So I have a sequence of random variables. I'm calling them XM. And this is a definition of them converging to their mean exponentially with a certain rate. And the definition is in terms of the probability that XM is far away from its mean being exponentially small with a constant C of n. Now, the way you always see generalization results, it looks more like this second line. And the way you get the second line is, there's the little one-line proof. You solve for delta, and you get what epsilon is, and you rewrite what that expression means. Okay, now, if my eyes don't like to see all those complicated things, so I like to simplify it and just say that this thing is order 1 over square root C of m with high probability, and know that that means that stuff with the square root of the log delta there. Okay, so that's the definition. When does it happen? So the simplest type of inequality is called Hoffding's inequality. I don't know if I'm pronouncing that right. It says you take Li. I'm calling these Li because in the future they're going to be losses. So losses at different data points. So a loss that's between 0 and C, IID with mean mu, that's the true expectation. And I'm going to define the random variable xm to be the average. That's all. If these are IID and between 0 and C, then xn converges to its mean exponentially with rate C of m. That's what Hoffding proves. And here's an immediate application to the tests. So if we say S is the test set, and we take a function, it could have been trained on a training set. It just has to be independent of the test set. And then we evaluate the losses. So Li is the loss of H at Xi and Yi. Then I'm saying we can apply Hoffding's inequality, and it's telling us that the test empirical loss is very close to the true loss. Okay, that's interpreting it. So it's weird because the data set are the Zs. The random variable is the loss of your model on the points. Yeah?
Because I guess at some point you will apply this to the documentation, but it's not going to be IIT anymore, no? As you said.
It's not, no, this doesn't apply to anything useful yet. This is just a warm-up.
Okay.
So this is only good for saying that the test accuracy is close to the true accuracy. It won't work for what we want. That was going to be my next thing. So, but what we care about sometimes is the generalization gap, which is the training loss compared to the true loss. And for that, we need to take it up a notch to McDiarmid's inequality. Okay? And what that says, we're going to have, and then there's a mystery function in here. The mystery function is going to make things work. So you still take your data set, and you take your mystery function, which is on the data set. I'll tell you what it is later. But you need to know that it has its own kind of stability, actually. You need to know that when you do replace one, so SI is where I've replaced exactly one point in my data set by another independent data point. Then we say that this mystery function f satisfies the bounded differences inequality if its value, when you change one data point, is bounded by C over M. Okay? So that's reasonable. And then McDiarmid's theorem says, if it satisfies BDI, then you still get exponential convergence rate. So everything looks the same now, but it's for this function f. Okay? And that's a hard theorem to prove. Now, a special case of this is Hofting's inequality, where if you set things up right, you take f of s to be the average, and each zi is actually li. Is there a typo or something confused?
I'm confused about the exponential rate.
Okay, that's my own little notation, so that could be. So starting at the top.
Yes, but if you get to your summary rate, I guess, yeah, it's exponential in probability, but it's okay.
Sometimes I get confused sometimes because often this is written with an m somewhere else and the m goes on the bottom. But then the s doesn't have the average. Is it the m?
I guess the dependence, the rate for the high probability, the delta of the high probability is exponential, but the rate of the expectation is not. Yeah, it's if you go to your theorem.
Yeah.
So the probability of deviation is exponentially fast with m. I think that's what they're referring.
Yeah.
Yeah, it's okay. I meant if you go to your results more down.
Okay.
Down,
McDermott's.
Yeah, McDermott's.
Okay.
Yeah, here. I was just a bit intrigued by xm converge to its mean exponentially. Because
because this is the restatement of the thing where xm minus mu less than or equal to epsilon is exponentially small and improving.
Probability.
Yeah, the probability of event. That's the probability that converge exponentially, but the deviation is actually 1/√m.
Yes, that's just what they call it, though.
I was intrigued by the exponential.
Yeah.
That's it.
No, it's the for the probability. I mean, yeah. I'm not going to say I can explain the terminology, but yeah. Okay.
Well, I can just say one word.
Please do.
It's kind of. It's off.
So the thing is, because you don't want to care about the probability of failure. So if it's exponentially low, then you can forget about it. That's kind of the idea. That's why you want exponential there.
Okay, so this is the magic fun part, which is what are we going to do? So first I'm going to show how stability approach and complexity approach are not so different in terms of constrained optimization versus unconstrained. Okay, so let's go back to what we're doing. Let's suppose that the problem we're solving is an algorithm of data set. You minimize an empirical loss plus lambda h norm squared, where h could be a function or a vector. A function in a Hilbert space, which is itself a vector or a vector. Bousquet will show us that that thing makes things stable, and you have the constant c over lambda m for the rate. Now, the other thing you can do is just hard constrain. Say, by some magic way, I'm going to make everything in my hypothesis class have norm less than or equal to capital lambda. Then this problem of just training over that restricted hypothesis class is constrained. Okay, because the constraint is hypothesis class constraint. Now, if you just know that there's going to be some Lagrange multiplier to that constraint, lambda, which is a function of capital lambda, you go back up and you receive the top thing. Okay, so in the theorem, in Wainwright or whatever, what they're often doing is saying, we're in a ball in this function class, a norm ball in the functions class. We're going to prove a complexity result. But in practice, what we're more often doing, well, at least in this case, what we're doing is empirical loss plus regularization. Okay, so the two are related.
Only for convex loss, though.
The loss does not, wait, that's a good question.
Constraint is more powerful. We'll reach some solution that is not reachable from any regularized approach.
Okay, that's a good question. In practice, we're fine with a convex loss. In practice, we're happy with one. I don't want to answer right now if the loss needs to be complex to get this to work, but I can talk about it after I'm trying to look at the proof. Okay, so here's the meta theorem, which covers two generalization proofs, the two most important ones. Define this magic function f of s. compute its expectation. Show f of s satisfies the bounded differences inequality, and then conclude from that inequality applied to f that you actually get what you want, that you have exponential convergence of the training loss to the true loss. Okay, that's the pattern of the proof, and the result will look like this. Yes?
Good question on where we are. Are you going to argue generalization for
Where it's going?
a case where you have data augmentation?
Yeah,
I see.
I want to, yeah.
Do you have independent?
No, don't
you have
need independence.
there?
Uh,
You need IID for my pyramid, right?
the data, well, let me just go step by step. It's hard enough. I'm already strained mentally by this. True. It's true. So let's show the pattern, but not do it for Rademacher complexity. Then when we get to kernels, that's where the sort of final part will come. So for Rademacher complexity, this is the magic function, that xm is my function f of s is the supremum over all the functions of the gap. Yeah, sorry, I'm going over if anyone needs to leave. So what do you get when you apply it? Thanks. What you get when you apply it is two big steps. You compute the expectation of that. So what is that? That's the worst case generalization gap over all the functions I'm allowed to use. That's how the dependence on the training set is removed, because instead of applying the inequality to your particular h, you just say, well, my guy can't be worse than the worst one. For the expectation, you actually get the definition of Rademacher complexity. That's what pops out. So it's and there's this subtle thing about complexity of loss composed with h or just h. I'm going to leave that for now. And then when you do the bounded differences inequality, what you get is a constant over m, where the constant is just the maximum value of the loss. Let's say the loss is between 0 and c. You get bounded differences. That step is actually not very hard. Oh, the screen went away. Did the meeting end? No. Okay, so that's an example of what happens for Rademacher complexity. Remember, we said this capital phi function, that's its expectation. But it also has the gap of your hypothesis baked in. So you prove my hypothesis can't be worse than Rademacher complexity plus big O 1 over square root of m. That's what comes out of it from doing these steps. And the type of applications now, then you say, well, when can I control the Rademacher complexity? And the two big examples are linear functions, linear with features, where you get that 1 over square root of m with constants depending on the size of the ball, the norm ball, and kernels, where now this is a function kernel norm, but it's the same inequality and actually the same proof. Okay, and now I like the stability theory one. What's the function for stability theory? It's the difference between the training loss and the true loss of what? The algorithm of S. So the function that is the outcome of your algorithm. So now when you do the bounded differences inequality, you're going to change one data point. You have to measure how much does that function change. And that's where replace one stability comes in. It's how much does the loss change and how much does the function change when you changed one point in the data set. So that also pops out the definition. It's not quite there yet. Hang on. So our algorithm, so E, the expectation gives you the expected leave one out error. That's what I was saying. And you can show that that's the generalization gap. And the thing you need, bounded DDD, the inequality, is the definition of stability. Okay, so now I'm running out of time. So I'm going to stop. Now let me just get to the punchline. Sorry. So in Bousquet, the paper, he does it for kernels. And now I want to show that it's not very far to go from kernels to graph Laplacian regularization. Now, when you go over the proof of the main result, you see that he applies it to a norm of h squared, norm of h in the kernel space squared. But the only time he doesn't need it, he applies, actually does it more generally, and you can apply it to any quadratic. So it could be m times h norm squared. And that m, when you make it our, what did I call it? The gradient operator, the graph Laplacian, the factoring of the graph Laplacian. That's a quadratic thing. I think I wrote down here. Here, application to SSL regularization. You just basically take the Bousquet theorem using n of h to be this, t grad of h squared, which is your graph Laplacian regularization. And the stability theorem basically works. That's basically it. So I'm just telling you a different way of proving a result that's in a paper, which gives you more intuition for what that term is, the assumption. It tells you that if I do graph Laplacian regularization, if I interpret my SSL algorithm to be graph Laplacian regularization, I obtain a stable algorithm. And that stability means it generalizes. Okay, that's the main thing to say. The second thing is we can interpret which functions we're going to learn now in terms of the data augmentation graph. So we're asking that the target functions be smooth, have a small Rayleigh quotient when you do data augmentation on them. That's what the condition is. Okay, so I'm going to stop there. Thank you very much. Sorry I tried to pack a little too much in, but it's an advertisement for taking my course or just talking to me. Thanks.
You have also some time for questions. For the mic.
Thank you, Adam. I really appreciate that connection to stability. So I think I have an inkling how you use it. My question is about independence, right? So if I were to take my data set of IID and I create augmented versions of each point, then I lose independence if I use them as individual points, right?
Right. That's not what, yeah, that's a really good point. So let's go back. So the things that are independent are the samples, not the random variables. So so here's what I do. I take my, so actually I have two data sets. I have the labeled points and the unlabeled points, but all that I consider one thing. For the labeled points, I apply just the regular supervised loss to it. But then I take all the points, labeled and unlabeled, and I put them into my graph Laplacian regularization. The points are IID. The original points.
Yeah.
That's my base.
Yeah.
That's my base of supervised, labeled and unlabeled points. The graph that I built, right, that's augmented images, that's only being used to connect edges of the base. So I lift them up to augmentations, I measure their overlap, and all those numbers get compressed back down into a connection between any 2 points. So the graph is over the IID points.
Okay. Somehow the strength of those connections depends on the points.
Yeah.
Right. So I wonder if that has any effect. But I think I see the point.
Yeah, we have 1 million IID points.
Yeah.
The new information is the weights connecting them.
Right.
And that was done in this complicated way where you go up. But I'm never saying these things up here. The augmented images are not points.
Which new information is dependent on the original points.
It is, yeah. But we're only using it to build up. Think of it this way. We have a data-dependent Hilbert space of or data-dependent norm that we're building that's doing the regularization.
I see. And you're saying that my Diarmid will still hold if you apply it for a Hilbert space, for a norm that is data dependent.
Okay, yeah, and that's also a really good point, which everybody kind of blurs over. So so there's two, actually, no, it's not blurred over. So again, this is technical. There's the true norm in the limit of, full expectations,
Yes.
right? And then there's the empirical Hilbert space norm, which is the one which we're approximating because we only did 20 data augmentations or whatever.
Yes.
And there's a separate issue of, am I converging from one to the other? And that's certainly not being addressed in this talk, but I've looked into it a little bit, and you do see, so if I needed to prove that, or something like that, the approach I would take would be a slightly different one. I'd go more towards the PCA proofs, the PCA interpretation, and use this big operator that you build, right? This big PCA type operator. There's two types of convergence. Does the operator converge and do the individual eigenvectors converge? The latter is harder. The former is actually not so hard. And there's proofs of concentration of measure in Hilbert space that people have used, older papers, people have used to prove these types of things that I looked into.
Okay. Okay.
So
That's good.
it's not addressed, but it's also not a hidden flaw. Let's put it that way.
So intuitively, if I were to stick with this style of stability analysis, would you expect that, yeah, there is some dependence between the metric and the data and McDermott, but as I take things to the limit, it washes out?
Yeah, I do. I think it's like this. It's like there's the true covariance matrix and there's the true, let's say, graph-Laplacian operator we wish we had.
Yeah.
And then there's an approximate one. And edge by edge, there could be some pretty oscillations. But overall, the operator that we're finding doing the regularization, I think, is a pretty good one. And I would try to do like more of a toy experiment to show that. That's something you can do.
Okay. All right. Thank you.
Good questions. I'm not gonna, if I give another talk in front of you guys, I'm not gonna try and slip anything by.
We're curious.
No, it's good questions.
It's a great direction, I think.
Question.
I guess your point raised the fact that there's two things going on. Is this a persuasive line of work, and is the story complete? And I think we're at the stage of, is this what matters? Is this useful and what matters? But the proofs are quite sketchy. If people decide that this is an important direction, I think there's a lot of things you could prove. The people who are strong in theory would want to prove to make it work. And you can take inspiration from some of the older stuff with kernels, but you need some new stuff too. I also like the question about when you might have data augmentations that have different roles with respect to labels, right? I think that's an interesting area to go. And what if some data augmentations will switch labels, do the opposite thing, right? What if a flip, not just a small rotation? It'd be interesting to put that into the loss too and talk about that, because I think that's
the questions. No.
Thanks a lot for this nice talk. Maybe I guess just going back to your last comment. So by choosing the data augmentation and having the data set, we fix this norm on the Hilbert space somehow. We changing what the balls look like, or in a soft manner, we regularize in a different way. And so how do you think this is like affecting, like in practice, like the choice of data augmentation? So because at some point we have these various regularizers.
Yeah, so
depending on how
I think this raised a key question that I'm actively looking for collaborations on now, which is the data augmentations were handed to you, but they were highly tuned, right? And so the real question for applications is, how do I solve the sort of hyper parameter problem of which data augmentations are going to be useful? for my downstream tasks. Now there's some information given by this, which is label invariance. With this, using this loss, it's label invariance that matters. Right? There's other less obvious stuff in there, which is you got to ask the question, what if all my data augmentations were just doing nothing? Everything becomes trivial, right? So you need enough data augmentation. And I think where that might come up is the spectral decay of actually finding the good functions, right? But there's a lot of things totally unaddressed and they were kind of buried. The paper, I guess a lot of deep learning papers are like, hey, we got this to work. And now you want to say, could I get this to work on a new problem? And that's, as far as I know, just trial and error, basically.
I can relate to that. And also back to the question that was before, somehow like in this generalization, theorems that you have here, you never look at the loss on the augmented data. You look at the loss on the original data, right?
Yeah.
So, but I guess by choosing the data augmentation differently, you would have like maybe some generalization property for the augmented data, which is not IID anymore, but you might be harder to actually, generalize to a harder set of augmentations, but at the same time might be good for accuracy on, performance on the original data. I don't know if there's any hope that
There's some
it's getting
subtleties.
inside.
So some authors present it like you only work with averages of augmented functions. That's how you kind of get around the fact that you're not really in RKHS. You have to push through and average everything. And we did simulations that showed if you do the data augmented version of your features, you get better accuracy at test time on test sets.
You mean averaging afterwards, like making it invariant?
If I define my features not to be just forward pass, but do all the data augmentations,
average,
pass through and average, then I get better accuracy. And that's consistent with the definition of what the function is supposed to be. And we looked into ways of also achieving that accuracy without having to do the data augmentations, which is kind of baked into this spectral. If you do actually get the orthogonal features, then you can look at eigen. Then you can just multiply by the eigenvalues if they really were orthogonal. So there's a lot you can do, actually. I'd like to do more stuff with this. I'd also, but I think it's quite wide open. I think there's been a few papers proving some nice results, but there's lots of questions left. And I think, there's not even an agreed, I don't know that people, I think there's lots to do.